What is that? What's going on?
We're going to catch some Pokemon. We're going to work out the maths behind catching Pokemon in the video game. Gotta catch them all. It's the motto behind the entire game. You'll have these fictional creatures. These are 3 examples. This is Eevee, Phanpy, and Pancham, 3 of my favorites. And the idea of the game is you go around, these creatures are in the wild, you capture them, you train them, you battle them. But ultimately, you're trying to beat all your other trainers and become champion, but you do that by catching all the Pokemon. Gotta catch them all. So there's maths behind how many different Pokemon you need to encounter before you can catch them all. Because if you encounter an Eevee, and you catch Eevee, let's say you're lucky, you find an Eevee, catch it, Eevee can appear again. So that wouldn't help you on your quest to catch all the Pokemon. So in the original game, the one I played as a kid, Pokemon Red, there are 150 different Pokemon to try and catch. And some of them, like Pidgey and Rattata, the pigeon and the rat version Pokemon, they appear all the time. And you would see probably hundreds of them as you play your way through the game because they're very common and they appear a lot. But ultimately, you're trying to catch all 150. So I'm going to ask the question, and we're going to answer this with maths. How many encounters do you expect to have in order to catch 150 Pokemon? Because it's going to be more than 150, but how big of a number is that going to be? So, in order to answer this, we have to make some assumptions. So in the game, you walk into the wild grass, which is where the Pokemon are located, and in different areas, different Pokemon live, and the rarer ones will appear less often than the common ones. But we're not going to model that, it's too hard. So we just assume that all Pokemon are equally likely to appear. As with any mathematical model, start simple, learn something, and then later on you can try and make it more realistic. So they're all equally likely to appear. And we're also going to assume that once you see a Pokemon, so once it appears for you in one of those encounters, you've caught it. Which again, for anyone who's played the game knows that is not how it works. Some of them run away, you kill some of them by accident. It's a nightmare. But again, keep it simple. If it appears for you, that's it, we're done. We're ticking it off the list. So, that's the starting model. And let's first focus on 3. We have 3 here. We can do the actual experiment to check the maths. Let's see how many encounters we would expect before we've seen all 3. And then we'll scale it up to 150. The sort of traditional number, and then we'll go big and do the 1,025 that currently exist across all 9 generations of the Pokemon games. So, n equals 3 Pokemon. If they're equally likely, the probability of any Pokemon appearing is going to be 1/3. So there's a 1 in 3 chance of seeing a species, let's say. Now, the first time you go into the wild grass, you're guaranteed to see a new Pokemon. You haven't seen any yet. So we're going to define something called Tn, and we're going to say this is the number of encounters until see new Pokemon having already seen n-1. Right, so we've already seen 3 Pokemon, and we want to know how many more encounters before we see our 4th. That would be T4. So T1 is, I'm looking for my first one. I've already seen 0. So how many encounters? 1. I go in the grass, I encounter a Pokemon, it's new. Simple.
And you've caught it.
And we've caught it, because we just have an unlimited supply of Master Balls. For those in the know, we have Master Balls, they never miss. T2. I have to think a bit more about this one, because the probability of getting a new Pokemon, well, I've already seen one of them. Let's suppose we've caught Eevee. Let's suppose Eevee popped up, we catch Eevee. Right, put Eevee over there. So we've already caught Eevee. But now, Eevee is still back in the wild.
There are other Eevees.
There are other Eevees. There isn't just one Eevee. There's another Eevee. So the probability of me...
And you haven't, and we're assuming you haven't depleted the stocks of Eevees by having caught one.
There's an unlimited amount of Eevees, yes. There's an unlimited amount of all of them, which I think is actually true in the game, apart from the legendaries, but we're not talking about legendaries. Probability of me getting a new Pokemon is going to be 2 out of 3. Because if Pancham appeared, I'm happy. If Phanpy appears, I'm happy. If Eevee appears, I'm annoyed. Already caught Eevee. Don't want another one. So it's 2 out of 3 chance. 3 total, 2 of them would be new. So that's the probability of me getting a new one. But that doesn't tell me anything about how many times it has to happen for me to, not guarantee, but how many times would I expect? How many encounters on average should I have before I see a new one? So you actually want to think of it as saying, well, let x equal the number of encounters until you get a new one. Within this setting, we're focusing on seeing our second one. Because then the probability that I get it immediately, the probability it takes one single time for it to happen is 2/3. I'm lucky. Straight away, I get a new one. But it could take me 2 attempts. So if it's going to take me 2 attempts, the first time I have to see Evie. Because otherwise, I'm done. But the fact that I'm counting it onto the second one means I must have seen an Eevee first. So there's a third chance that I see Eevee, and then I get the 2/3 from having seen one of the Pancham or Fampi. And then that could also, though, it could take me 3 attempts. So I could see Eevee the first time, and then I could see Eevee again, so it's a third squared, and then I get my new Pokemon. And this pattern's going to continue. And the probability that it takes me k such encounters, you can hopefully see the pattern, is a third to the k-1. I have to fail in the first k-1 attempts, and then I succeed. So this is what we call a geometric distribution. And this is going to be key because we want to talk about expected numbers, means, averages. You need to know the distribution before you can talk about those things. So this is what we call a geometric distribution, and here the parameter is 2/3. It's the one, probability of success is the parameter that defines it. This parameter is the probability of failure, which is 1 minus the probability of success. Generally, what this looks like is the probability x equals k is we have to fail, so that's 1 minus p, fail, k-1 times, and then succeed once. So p is the probability of success, that's our 2/3, 1 minus 2/3 gives me a third of failure. So that gives us the probabilities of getting our first new Pokemon, our second new Pokemon, but we still need our third new Pokemon. We want to know how many encounters should there be there. So the key thing is, up here, we said the probability of a new one was 2 out of 3, because we'd seen Eevee, so then it were 2 out of the 3. But now we've seen Eevee and we've seen Fampi, so there's only 1 out of 3. So the probability's changed. So this, we can immediately just say, actually now, it's a geometric distribution again, because nothing about how we encounter them has been changed, except now the probability has. It's only a third. So this was like probability 1, probability 2/3, 2 out of 3, probability 1 out of 3. And so we know the distribution again. And then we stop, because we've seen all 3. So that gives us now a way of tracking the total number of encounters. The amount of times we have to walk into the wild long grass and battle Pokemon is given by 1 at the beginning, plus the number that we had to get our second Pokemon, plus the number to get our third. And in this example, we're only interested in these 3, so we would stop. That would be all of the 3 Pokemon available in the world had been caught. That would give us the answer if we had the values for these, but we don't. We want to know the expected total number. So that's 1 plus the average of that one, the expected value of that, plus the expected value of the third. So this means basically is like the average number, or the mean. Like if we were to do this many, many times, at which point would we, like, on average, would it settle down to? How do we calculate the expected value of a geometric distribution? And for that, we need more paper. I think the best way to understand expectation is to actually think of an example that probably everyone in the world is familiar with, of rolling a die. So the way you would do it for a dice is you say, well, I can roll a 1, and the probability of me getting that is 1/6. So there's a 1 in 6 chance that I get a 1. But then I could get a 2, and there's a 1 in 6 chance I get that. I could get a 3, and there's a 1 in 6 chance, all the way up to I can get a 6, and there's a 1 in 6 chance. So there's a 1 out of 6 chance that 1 gets added to my total, 1 out of 6 chance that I add 2 to my total, 3, 4, 5, and 6. And this is actually going to be, and I'm sure many people watching this will know, this comes out at 7/2, which is 3.5. The expected value of your rolling of your die is actually 3.5. Lots of people think it's 3, but of course you can't get 0. So it's a 1 and the 6. You kind of add those together and divide by 2, gives you 3.5. So it's sort of, you know, this is the formal way of doing it, but it fits a lot with our intuition of like averaging of the numbers you could get. But this is important because this is how you work out the expectation. So what you're doing here in this formula is you're taking your value on the die and you're multiplying by the probability of getting that value. And then you're adding them all together. And that's exactly how we define the expectation of a probability distribution. So we say x is a probability distribution. The expected value of x is the sum over all values of the value it can take times the probability that it is equal to that value. And this is over all allowed k. So in the die, this could be 1 through to 6, for example. But that'll change depending on the situation you're modeling. Now, back to geometric distributions, back to Pokemon. We know this. We cleverly wrote this down at each of those stages, as you have to have failed k minus 1 times, and then you succeed on the kth encounter to see your new Pokemon. So for the Pokemon, and we did it for T2, didn't we? How many encounters could you have? Well, there's no limit. You actually go to infinity. You could just be super unlucky and keep seeing Eevee after Eevee after Eevee after Eevee. It's not likely that it could go forever, but it is certainly within the realms of possibility. You have that much bad luck. So you actually need to sum to infinity, and then it's k, and then we had a formula for this, which was 1 minus p to the k minus 1 times p. So now we've got an infinite sum that we have to work out, which looks terrifying and very difficult to do. It's actually not as bad as it first looks, and I will give you the key steps. I won't go through a full proof of how to do this sum, but I will show you the key steps because I think they're really nice, and it's one of my favorite proofs. So it's very similar to a geometric series. So we have an infinite geometric series, which is where you have something like the sum from k equals 0 to infinity of a times r to the k, and we know that this is a over 1 minus r whenever r is less than 1. So again, don't worry if you've never seen this before, but this is a reasonably well-known formula for summing together infinite pieces that you often learn about at school or definitely at university. Now, this does not quite look like what we've got. So first thing we can actually match up is this and this are the same thing. So p here is just our a, it's a constant term, it doesn't change with the sum. But then these bits, we've got something to the power k, and here we've got k times something to the k minus 1. So they don't quite match up, so we can't just use the formula. But, and this is the clever part, we differentiate the series. So if you differentiate both sides of this equation, the left of it is the sum from 1 to infinity of k a r to the k minus 1. You bring the power down, reduce it by 1, and then you differentiate this function and you get a over 1 minus r squared. So this is now exactly what we've got up here, because p is ra, our thing to the k minus 1 is 1 minus p, and we've got the k term that we didn't have before. So we have a formula for this, so we can sub it in, where, so for this, we've got a is p, so it's p over 1 minus r. R is 1 minus p, so 1 minus that actually just gives me a p. So the answer, unbelievably, is 1 over p. So, now some of you who've come across...
I felt like I was in that long wild grass then, but anyway, right.
So, some of you may have already known that for a geometric distribution, the mean is 1 over p. And you could, of course, just use that to get us the answer. But it's one of my favorite proofs, so I was going to take the opportunity to tell you about it. What does this all mean for Pokemon? Right, this is the key thing. So we've got our 3 Pokemon, and we said the expected number of encounters was 1 plus the expected number to see our second one plus the expected number to see our third one. Now, the second one we said was geometric distribution, parameter was 2/3. This one was geometric, parameter 1/3. So the expected, this is p, changes, but we know the expectation is 1 over it. So this one is plus 1 over 2/3 is 3 over 2. 1 over 1/3 is 3. So the answer is 1 plus 1.5 plus 3 is 5.5. So to see 3 different Pokemon, you would expect, on average, to have 5.5 encounters. Of course, you can't have half an encounter, so it's telling you it's going to be somewhere between 5 and 6. But when you're playing the game, if all of them were equally likely, you would expect, on average, to have between 5 and 6 encounters in order to see 3. So obviously more than the 3, right? You could do it in 3, but it could also take you 400 if you're really unlucky. But on average, it'll settle down to like 5.5. All right, well, I thought we'd do a live action, let's say, attempt to catch some Pokemon.
Let's see if it takes us 5 or 6 or...
Exactly, we figured out how many it should take us. So what we're going to do is I have in here various coloured counters. So red is going to mean an Eevee, blue is going to mean Phanpy, yellow is going to be Pancham. So I'm going to draw the counters out. I'm going to have to put them back because remember, they don't get removed from the system. But let's see how many it should take for me to get the 3 different colours. So, first one, red.
Oh!
Right, so let's get rid of the... We've caught Eevee.
You gotta.
Simple. If only Pokemon was so easy. Right, Eevee appears, Eevee is caught.
What's one?
Goes back in.
One.
One so far. Yellow. There we go. Pancham joining the team.
2.
I'm going to set myself up for disproving my maths now, aren't I? Right. Ah, to Pancham again.
Oh, all right. 3.
Ah, 4. We're done. Fampi, 4, blue.
You beat the odds.
I beat the odds. So it wasn't perfect, but you know, I think it wasn't. I didn't get a 3. It showed it's going to be more than just simply 3. So I did it in 4, which I think is, you know, I was lucky. I beat the odds, but if I were to repeat that again, it's probably not going to be 4.
If only the Pokemon universe was so small.
Yes, if only there were 3. But there aren't 3. There are 150 in the original and 1,025 in the latest generation, with them all included. So we want to know what happens for a general n. Same idea, but let's work it out for n, and then we can sub in 150, and let's get a formula for that. And then, well, if we subbed in n equals 3, we'd get back to 5.5, and we'd get all our other stuff. The same idea holds, right? First time I go into the grass, I see a new Pokemon. The second time I go in, so we know it's a geometric distribution. And if you remember here, the probability of a new Pokemon was 2 out of 3. But now, I have seen 1 out of n possible Pokemon. So there are n minus 1 out of n remaining. So it's a geometric n minus 1 over n. And again, if n was 3, that gives you your 2/3 that we had. So then the next step, we've seen 2 now. So this one is n minus 2 out of n. And again, when n was 3, we got a 1/3. Then before we stopped, but now we're going to carry on all the way up until we see the nth one. And that's going to be geometric again. And this is going to now be n minus 1, because you subtract 1 smaller than the number there over n. But that is, of course, 1 over n. Because there's only 1 left that we haven't seen at that point. We've seen all the other 149 if we were doing the original. So the total t is the sum of all of these. So the expected number is 1 plus the expected number of t 2 plus all the way up to the expected number of the last one. We now know how to do the expected value of a geometric distribution. We went through one of my favorite proofs, sort of. So we know that this is 1 over this number. So it's n over n minus 1. And then ... and then this one is 1 over this number, so flip it. So you just flip the probability. So what have we got? We've got 1 plus n over n minus 1 plus n over n minus 2, pattern continues, plus n over 2 plus n over 1. Now, there's a lot of n's floating around, so let's pull that out. And then in this bracket, I'm going to flip the order I'm adding them. And you know what? Now I've said this, let's call that n over n, and then ignore that. So I can pull out an n, and then what I've got here is 1 plus a half plus a third plus ... plus 1 over n minus 1 plus 1 over n. So I've swapped the order, so just to point that out, because it is important. So I had pull out the n, and this is a 1 over n, so I've put that one at the end, and then this one down here, etc. So like this one has gone down here. Flip the order, but it's now in a nice decreasing order. But now it looks like something that some of you watching this may have seen before, because what we've got is n times the sum from 1 to n of 1 over k. And this is what we call hn. It's the nth harmonic number. You're adding the reciprocals of the numbers. Now this sequence, as n goes to infinity, this goes to infinity. It's quite a famous mathematical result that 1 over each number, 1 plus a half plus a third plus a fourth. The fact that that's infinity is mind-blowing, and even to me now it feels mind-blowing that that actually gets you to infinity. But we're obviously not going to infinity, we are stopping somewhere. This is hn and it's multiplied by n. So we can say the total number of encounters, the expected, I should say, the average or the expected total number of encounters is going to look like n times this nth harmonic number. Now, what do the harmonic numbers grow like? How big is this going to get as we increase n? Because we want to sub in n is 150 or 1025. So my favorite way to see the growth of the harmonic numbers, if we plot what we've got here. So this rectangle, width 1, height 1. So this has an area of 1. This rectangle, width 1, height a half. So this has area of half. This is area of third, etc. So the area of all of these rectangles added together is the same as adding together n of these numbers. But if I put dots here and I draw this curve through them, this is 1 over x. That's the graph of 1 divided by x, because 1 over 1, 1 over 2. This area is bigger than the area underneath the graph. So if I put the graph in red, that's the area underneath the graph from 1 up to some point n. So we can say that this number is bigger than the integral from 1 to n of 1 over x, but that is actually going to be the natural log of the number n, and that tends to infinity as n goes to infinity. So the point is, this goes to infinity, but the numbers we're adding are bigger than this thing. So therefore they have to go to infinity. So all told, we can say the number of encounters of our Pokemon looks like n times the natural log of n. So when n is 3, this is about 5.5, what we calculated. Pretty good approximation. So when n is 150, how many encounters? We're going to actually expect to have 752. So we saw that when we had 3, it was less than twice. But when we have 150 Pokemon, it's almost 5 times as many encounters.
That's less than I expected.
Well, that's with them being equally likely, and that's with us catching every single one. But as someone who plays the game, to think that I've had probably a minimum of 750 encounters when playing the game, each encounter is like a minute or so. It's quite a lot of time I'm spending trying to catch Pokemon. But then when you go to 1025, the current total number of Pokemon in the game, you're actually going to have a total number of encounters of approximately 7,106. So to catch, that's like, I would say this is very much a lower estimate. But if you're playing Pokemon and you want to try and actually catch all of them, all 1025 in the latest generation, across all the generations, you're going to actually have to battle and encounter, I'd say a minimum of 7,000 to realistically have a chance. That's the expected number for this very simplistic model where everyone appears as often as the other. The fact that that doesn't work that way means this number will be higher.
Have you caught them all?
I have caught the original 150, but I don't think I ever completed the Pokedex in any game except Generation 1, because it's too many. Because they just add, it's like you need all of the old ones, plus all of the new ones, and like, I've completed the game in terms of being the Pokemon champion. So I value battling more than catching them, I guess. But I did it on the original one several times. I remember doing it when I was like 6, and then I did it again a few years ago because they re-released the game, and I spent several weeks playing Pokemon as a 32-year-old and loved it.
A big thanks to all our Patreon supporters, including those people whose names you see on the screen at the moment. You can support us, help us make more and better videos, and we also occasionally give you access to sort of bonus material and other goodies. Find out more on our Patreon page. Go to patreon.com/numberphile. There's also a link in the description.